Okay, we still have some stragglers having time. So in a sense, what we have done is to try and project that time series of observed temperature change onto whatever is human-induced and natural only. Okay? So, but how do you know where the natural warming came from? Where is that blue curve coming from? Right? It could be one model into which you gave all the natural forcings and it produced some version of this blue curve, right? Or the same model might have given you that origin. So if you put a different model and give it the anthropogenic forcings or the natural forcings, the shapes of these curves would be slightly different. Okay? So, which means some of this and the way you projected it can depend on which model you are using, right? So, so when I do this, the two-dimensional projection, and I get this sort of inclined plane which has some slow gradient on each of those axes, that can be changed depending on which model I use. Okay? So, ideally I should see whether it changes if I use this model or that model. You can actually do that. And you can actually say, okay, here's one gradient, here's the other gradient, and if you've done any simple thing like a linear regression, you know that there is some uncertainty, right? How many of you have done linear regression, fitting a slope to a line? So if you just returned slope and intercept, you were wrong, right? You have to also report the uncertainty in that slope and that intercept, because there will be some error bar associated with it. So you can account for that and say, so this is what we call scaling. Okay, that slope that we had on each of these two planes, right, on the human-induced and on the natural, those are the two numbers that I can now plot in a regular two-dimensional plot, which I am calling. So 0.9 and 0.7 scaling on the natural warming, right? That becomes my point. Okay? So that plane is described by that point. So these are what I call scaling factors. Okay? So essentially this point is so close to 1, 1, right? When it's close to 1, 1, it's essentially telling you that this is a linear combination of that blue curve and that orange curve with almost equal weightage in order to get the observations. Okay? So all you're doing is you are linearly adding up those two curves with some weightage. Okay? Now, if it were exactly 1, 1, that means those two curves are exactly, you add them up and you will get the observations. Okay? In this particular example, you have to weigh the natural forcing by 0.7 or the response to the natural forcing by 0.7 and the response to the human-induced by that in order to get the observations. Okay, and this sort of ellipse here includes the spread of possible points, depending on which model you use and what uncertainty to that slope that you take. Now here is another cloud, which is how would you scale these two, the natural and the human-induced, in order to get a controller. Okay? So it turns out that this scaling is about 0. So a control run has almost no human-induced warming and almost no natural variations like the sun or, okay? So this is one way of representing. So you see how this red ellipse is completely separated from this black ellipse. If these two are intersecting, then you can't distinguish them, right? So this one is saying that the observations are best described by these human-induced and natural warming with that scale. That scaling is completely different from the 0, right? So this is also important because if you cannot distinguish no natural forcings or no human-induced forcings from the run with both human and natural forcings, then essentially it means you are not able to attribute. Okay? There is no separation, means there is no real detection of change, but also there is no attribution. So you can actually do that instead of natural forcings. I can just put one of the natural forces. I can say only solar radiation. I can put only land-to-land change. Okay, so I can see which variation is giving me how much attributable. So this human-induced warming is at 0.9 with some that crossbar is giving me error bounds within it. And this natural variation is giving me 0.7 with some plus minus, right? So if I look at this is what we describe as an attributable warming change. Okay? So the observed warming since, I think this is since 1850, I forget, but it's a figure in the IISc chapter 10. So this is the observed warming with some error bars. If you use only greenhouse gases, that represents a warming actually more than the observed. Okay? So if you had a run with greenhouse gases only and no aerosols, you would actually get a warmer temperature. It's because you had aerosols, which are also anthropogenic, that you actually end up with anthropogenic and observed being close to each other. But if you only had greenhouse gases, you would have a much higher temperature change. So I can actually attribute that greenhouse gases are causing more warming than actually observed. Okay? Because my anthropogenic includes some of these things, the ones that are doing the cooling. Things like land surface change is a net cooling, aerosols are a net cooling, right? Both of those are adding on to this greenhouse gases and providing this thing. If I only take natural forcings, okay, you remember how that blue line was just around 0, right? The net effect of natural variations is that it has a 0 effect on temperature. Okay? Yeah. And internal variability is something again you can separate out. If you have no forcings at all, then internal variability is your factor that is accounting for temperature change. So you can actually say internal variability also is centered around 0. So you can attribute 0 warming to natural stuff, 0 warming to internal variability, more warming than actually observed to greenhouse gases, and anthropogenic is slightly more than observed. Okay? Fine? Yeah.
So, what is the difference between natural and internal variability?
So, there is a notion of what is internal to the climate system and external to the climate system. Okay? So, I can define any system with like a closed box, right? So, anything that happens within that box, and here, don't think of the box as, oh, it's the earth. Okay? The box is the climate system. Okay? So, anything that is within that climate system, like clouds and rainfall and oceans and atmosphere, all that is within the climate system. Vegetation, plant surface, all of that is going to change naturally. But that is what we call internal to the system. Okay? So internal to the system would be atmosphere, ocean, land, and everything connected with that. Now, when I say natural in this context, a natural can still be external to this system. Okay? So if I change solar radiation, okay? Solar radiation is not within your climate system. Its radiation is coming into your system and your system is responding to it, right? So when I change this, that is an external force. Okay? Similarly in volcanoes, even though a volcano exists here, inside my earth, what the volcano puts out is a forcing which is accounted for as external. Okay? Are you following? So it's you have to separate out the physical boundary of a volcano from the effects of a volcano. The effect of a volcano is that it is going to affect your climate system. Okay? And it is not in turn affected by climate. Right? Your solar radiation is not affected by climate. Right? The sun is doing what it does. It is not affected by climate. Right? Similarly, volcano is doing what it does. It comes and goes. It's not affected by the climate. Therefore, it is not considered as part of the system. Your anthropogenic CO2 emissions is not really coming from climate. Right? Yeah.
Last century, two major volcanic eruptions caused significant reduction in global temperature.
Yeah.
Still, our natural pattern is showing that this attribution is 0.
So, it is for warming, present warming in relation to 1850. That is it. Those volcanoes had an effect, for a few years, but in the long term, that effect is now gone. The change from 1850 to 2010 is this black bar, right? To that black bar, there is no effect from that volcano. Okay? Volcano effect is short-lived. Okay? Yeah.
Sir, in case of the aerosol forcing, the black line is like bigger than the actual forcing.
Yeah.
So, like how then actually like that part is like basically how confident we are?
So, essentially, this black line is your confidence interval, right? Not your uncertainty. So, if you don't know all the aerosol processes very well, each model essentially is simulating a different sort of an effect. And that aerosols are really poorly understood in the grand scheme of things. But even more poorly understood is how clouds interact with aerosols, which is also over here. So those two combined make for, essentially what this error bar is telling us is that we don't know the sign very well. Okay, this is the amount we can attribute with this error bar. It could be that there's actually a slight positive contribution. I'm sorry, I'm unable to hear you. Yes, volcanic forcing is always an external forcing to the climate system.
Then when you do applications without observations, observations will always have
Yeah. So, I mean, so if I stand out in the sun, okay, my body temperature is going to go up because of the external force, right? So that doesn't mean that my body temperature can't change due to other reasons. There could be internal reasons for it to change, right? So similarly, when I have a volcano go off and affect the temperature, my climate system, internal, external, is only as far as the radiation balance at the top of the atmosphere. That is the consideration, okay? But the temperature measurement itself is a combination of all the external forces and internal variability, right? So all of those are actually combining and producing my actual observed temperature, okay? So out of that observed temperature, what is the contribution of a solar radiation or a volcano or something else? That is what we are trying to do. Okay? It is like essentially trying to say, okay, my bank balance went up. How much it went up, I know. How much of that increase is because I won the lottery or I got an increase in my stipend or something else happened. So you're basically trying to quantify what those contributions are, right? So that's the exercise. They're all, your bank balance is a function of all of those things, right? And what you spend, all of them. Okay? Maybe 1 month you can go out to eat or do anything. Maybe that's why your bank balance went up, right? So what is internal, what is external is as far as the forcing. Once you put the forcing, it's all the system response. Okay? So your temperature response is a function of the system and the forcing. Okay? Fine? So I will not claim that this is easy to understand. Getting into the rigors of how you calculate all this can send any sane person crazy, okay? So it is quite complex. I don't want you to assume that it's all easy, yet I don't understand, I don't know what's going on. It's not easy. It could be a full 1 semester course, okay? Trying to say it all in 3 hours is hard. So, what I'm going to focus instead is, okay, so this is just a simple example of how you do projection and what do those numbers mean, okay? So you're basically saying, I have these two kinds of forcings, one is natural, one is anthropogenic. If I combine them, weighted, I will get my observed curve, right? So that is what a scaling is, and that scaling therefore can tell me if the scaling is 0, that means something is not affecting anything at all. Therefore, so if I get to what the actual things that are where detection and attribution have been carried out. So, I mean, the example we took was of global mean temperature. Okay? So, you can do this not just with the global mean temperature. You can say, I'm going to actually see how the pattern, okay, spatial pattern of temperature change has varied over time. Okay? Because that is not a single line. That will then be a spatial map varying over time, so your problem has a different dimensionality. Okay? But if you were to look at things, now here's surface temperature over North America, Europe, Africa, Asia, South America, Australia. All of these places you've seen this kind of a curve before, where the natural only run does not explain the observation, but you have to have natural and anthropogenic. There's also ocean heat content here, where some work that I've been involved in has looked at different ocean bases. So this is the Southern Ocean, South Pacific, North Pacific, North Atlantic, South Atlantic, where ocean heat content also is showing that separation between. Okay? Now, one of the things when Dr. Bala started with the introduction today, he said, you know, somebody reports, oh, it rained or it was so hot this summer because of global warming change, right? So, but I just finished telling you in the global mean, you're able to say something. So, but when you say something, can I say something about Bangalore climate or somebody somewhere else? So, the question that in the latest IISc report that we tried to answer is, how much should the global mean temperature change before you start feeling a temperature change in your location? Okay? So, how much should global average temperature rise by before me living, I live in Delhi, you live somewhere else, each of you lives in a different part of the country, when will you feel that the climate has actually changed? Okay? So here, I'm going to show you map first. So there are 4 locations pointed to. There are 2 sort of low latitude regions, right? One in South America, another one in Africa. Yeah. So if you look at these arrows are pointing there. So this is a high latitude region. This is sort of the mid latitudes here, right? So, what do you know about the temperature in these different locations? Between, say, some place on the equator versus some place in the high latitude, where do you think the larger temperature swings are? Near the equator? How much does Bangalore temperature vary? How much does Kerala temperature vary? How much does Delhi temperature vary? We think the temperature variations are small where? Sorry? Near the equator it will be smaller. Desert. So there are variations on all time scales, right? Day, night, you will have variation. Diurnal temperature range. Seasonal temperature, winter, summer, temperature will be there. Then there will be year-to-year incremental temperature change, decade to decade, right? So, if you go to a desert, what will be a large temperature range? Diurnal temperature range will be large, right? Now, if you go to a coastal area, your diurnal temperature range will be small, and your seasonal temperature range also might be small. Okay? Depending on where. So, similarly, interannual temperature range can also be different. As you go further towards the poles, away from the equator, your temperature swings in the seasons are larger. Okay? One season there is no sunlight. Right? Few months completely dark, and then 24 hours sunlight. It will do crazy things to the temperature. The range and seasonal range of temperatures is huge. So, year-to-year temperature change variation will also be large. Okay? So, if you look at this blue line and this orange line, okay, for these four locations, in this region, you find that the band is larger. Yeah? The width of the band is much larger. Okay, so this is essentially saying, if I look at the blue curve, that is my December, January, February temperature anomaly. So every year I take DJF temperature anomaly and I plot it, then it looks like that. So this is a range of values. This band is representing the range of values possible. So when I'm close to the equator, in these two locations, as opposed to far away from the equator, that range is much smaller near the equator. Okay? So, for me to say some climate change has happened, there's actually a color missing in this plot. Okay, so there's a gray band here, okay, which is sort of a continuation of this part of these curves. Okay, so you can think, if you keep going straight, horizontally, right, that would be your band with no anthropogenic force. Okay? So at some point, your orange curve is going to separate from the horizontal black band. So I know these slides have been provided to all of you. Please look at that because somehow on this screen that color is not being shown at all. Okay? So imagine a gray band here, a gray band here, okay, flat. It's going to be centered around 0, okay? And so I have a, so this would be, okay, so this is a gray band which represents the range of natural variations within temperature in a particular region. Now, once I start giving it greenhouse forcing, I am going to produce temperatures that start increasing and deviating at a certain point of time. Okay? So, if my band is y, this y, then this separation, even though my beam starts separating here, this is going to be only clearly show separation at this time T1. Okay? If my band is much wider, if the natural variation in temperature at a particular location is much more, then this separation will occur at a much later time. Okay? So, and much later time means much higher temperature change in the globe. Okay? So this blue color here indicates what is the global temperature change, at which point your anthropogenic force change will separate from natural change. Okay? So you have to actually change temperatures here by more than 1 degree centigrade. The global mean temperature has to change by more than 1 for us to distinguish here. Whereas over here, there is probably already detectable change because, so in essence, this width of this area that we are talking about, the natural variations that can occur, is really noise. Okay? So, if I'm trying to teach a class here, there's some guy doing some work there, banging anything. There could be another guy doing something else there. There's all kinds of noise, right? In order for me to make myself heard, I have to amplify my voice. My voice has to go beyond that noise, right? For you to hear it. Similarly, if the natural variation is a lot, if my bank balance goes from 0 to 10,000 rupees within a month, every month it is going like that. For me to feel rich, it has to really cross that 10,000. It has to become 15, 20,000 for me to feel like, oh, I'm rich. Right? Because anything that happens between 0 and 10,000 is noise. Anything that is coming from outside. Okay? For me to say, I can hear something clearly, it could either be by amplifying the signal, right? Signal has to be more than the noise, right? So I can amplify the signal or I can beat down the noise. If I stop all that external noise, then it's much easier for me to hear it, right? So you can either reduce the noise or amplify the signal. So in essence, that signal to noise ratio is what determines whether something is going to be audible or not. Okay? It's not just the volume of the signal or just the volume of the noise, but the ratio of that signal to noise. Okay? So, this noise, the width of that band, because it determines whether or not I can detect a change is an important thing. Okay? Because right now, how do we know what the noise is? We can only know that from models where we do not impose any external force, right? Anything that is internal variability is our noise, okay? No external, natural or anthropogenic. Those don't count as noise. It's anything that is internal variability is my noise, right? So, how do we know that envelope of variability in our models is correct? Okay? So, if we are wrong, if the actual noise is this much, but I am assuming it is this much, then clearly I will end up with wrong results. Okay? And the amount of variability, therefore, has to be known to be correct. Okay? So, that's why we do what is called climate model evaluation. Okay? So, climate models are the only tool we have for making climate predictions into the future. Okay? You don't have any other real technique, right? These tools, as I have discussed, have 6 systematic errors. Okay? So, when you have something that has errors, these errors limit our ability to make reliable forecasts of the climate changes we may experience. Okay? So, if I know that some model that I have it's okay, it works within some parameters, within some range of values, I get good results. But beyond that, I don't know if it's still a valid model. So because of these reasons, and in our context, the ability to estimate what we call internal variability correctly, right? That's why we do a rigorous model evaluation. Okay? Model evaluation is, we look at, okay, is the mean climate being simulated? Is it the climate of Earth? Or am I getting Venus? Okay? So it has to be something that's a realistic mean climate of the planet. The diurnal cycle. Okay? If I put sunlight, is it giving me the temperature rise and fall at night and dusk in the correct phasing? Is my rainfall occurring in the correct time of day? Is my land sea breeze occurring at the correct time of day in the correct location? All of these are important. Seasonal cycle. Okay? Am I getting cold winters and warm summers, or am I getting the opposite? So, all important to check. Interannual variability. Right? Things like El Nino, North Atlantic oscillation, all of these are naturally occurring modes of internal variability. If my model does not have El Nino, okay, which is considered the biggest, largest interannual variability mode that exists, then, if it's missing a key aspect of variability, should I believe that model? Right? It may have other mistakes that make it a worthless model. Then we also look to see how it has simulated climate of the past. So this is where our historical run is evaluated against observed records of climate, right? Climate of the distant past, right? Like at the last glacial maximum. So you want to make sure that under completely different orbital parameters, different CO2 concentrations, that the model is actually producing the glaciated Earth. That it puts ice and snow where it used to be. Okay? It can't still produce the same climate as today if you give it the forcings from 20,000 years ago. Okay? So, and then we all know about these modern comparison projects. So, these are mainly intended to, it's like a Miss World or Miss Universe contest. I make them all do the same things. Some talent show, some this, some that. They're all trying to do the same exercise, and there's no winner at the end. It is just, it's a way of understanding what is good about your model, what are the deficiencies in the model, whether this set of models are useful for certain kinds of things, right? Whether you can trust it when you go in for a projection of climate change into the future. So you do things like compute the annual cycle and phase, amplitude and phase of different variables. So there's surface air temperature, there's 2 meter air temperature, and there's precipitation, that's outgoing long wave radiation. So you can actually, this is what the observations are, this row, and then this is a mean model. So you kind of get an idea of what is the collection of models. Do they all have the same kind of error? Is there a different error in each model, or are they all deficient in some common way? Okay? That's one kind of question you can ask. You can also just do, I'm sure most of you, any of you who used any model and looked at the output and say, okay, this is my reference or observed data set, and this is my model, then I'm going to plot the difference, and that's going to tell me, where is my model weighing too much, where is it weighing too little, okay? Because those give you an insight into what processes might be wrong. And you can also do similar things with ocean heat content. You can plot the annual cycle. You can also do sea ice. Again, month by month, you can look at that. This is the observed concentration, and those are 3 separate models, and you can actually visually inspect this and come to whatever conclusions, and then you can do things like, this plot is also fully washed out for some reason. So this is power spectra, okay, for the Nino 3 temperature anomaly. Essentially, this is the region where you see the El Nino oscillation. So you say, okay, is it coming in the right periodicity at the right intensity? Okay, so anything that is showing an oscillation away from the sort of peak that's observed here, it's also too intense here. Those are telling you that there's some problem with those models. Whereas many models seem to follow what's observed. So, and some of this is just, you can't make decisions whether a model is good or bad based on just visual observation. So you try and do sort of quantitative comparisons. You can actually color them and say, okay, I'm going to compare all these models to, say, the IISc analysis, and these are different metrics, total error, which I can break it up into many different components in that sense. And if it's a good low error, it's good. Okay? So anything that's blue is considered good. So I can say that some models seem to have more red. Okay? So this is like your homework or whatever. Lots of reading is not good, right? So similar such things have been done here. And then, you know, one doesn't know if entropy analysis is any good. There are other options. So you can actually do this. One half of the square will be reference will be one observational data set, another one will be another. So there's a lot of effort that people put into understanding whether a model is any good or not. Okay? You have to know whether your model is producing anything that is realistic, first of all, and then how realistic, how well does it do a whole suite of range of things. Okay? So then let's skip this part. So I don't have time to explain what a Taylor diagram is, but what I'm going to do is skip ahead to. So, how many of you know what the tropopause is? Okay. What is tropopause? Layer above the troposphere? Okay, it's the transition from troposphere to stratosphere, right? So within the troposphere, what happens? Temperature drops, and in the stratosphere, temperature increases to 5, right? So your temperature curve here actually has an inflection, right? So if you take actual data from insect and curve analysis, so this is in the tropics, your temperature changes direction there. So I am going to designate this point where the temperature changes as my tropopause line. Okay, so that corresponds to some pressure level, right? So why is the temperature increasing here? Ozone. So for chemistry, ozone chemistry is occurring, and therefore you end up with temperature increase, right? So now, what would happen if I increase CO2? CO2 is a well-mixed gas. What happens in the atmosphere when I increase CO2? Troposphere, sorry? Temperature will increase. Where? Everywhere? So, I expect a temperature change, positive temperature change in the troposphere and negative temperature change in the stratosphere. Okay? What happens if I have a volcanic eruption? So I'm essentially putting some sulfate aerosols up there in the stratosphere, right? So what would happen to temperature? So I'm going to have a reduced temperature at the surface, right? But what about troposphere and stratosphere? Troposphere, it won't change? No change? It will change? How? Increase or decrease? Decrease. What about stratosphere? It will increase. Okay? So remember this. A lot of opposite effects. Okay? So we can represent that here. Okay? Now, if this black line is my nominal temperature profile, right? It's not from observation, it's all straight lines. If I increase CO2, I'm going to move this black line to the right and this stratosphere to the left. Okay? Which means my tropopause might increase. Okay? Again, some colors are missing. So here I have, this is my nominal temperature profile, right? So then I increase CO2. So my stratospheric temperature decreases, right? But my tropospheric temperature increases. Previously, this was my tropopause height, and now this is my tropopause height. Okay, so essentially, my troposphere expanded, right? So my tropopause height went up. So there's a change in pressure level. Okay? So the height went up means pressure decreases. Okay? Now the opposite sort of thing is happening here. Volcanic eruption. I have that, and if I reduce tropospheric temperature and increase stratospheric temperature, then my new tropopause height is here, the old one was there. Yeah? So my tropopause height actually decreased, which means my tropopause height pressure increased. Okay? So, if I were to run some climate models with individual forces, now I am going to give only natural forces, which would be, there's no CO2 in the natural, right? There's only solar radiation and volcanic eruptions. Then I'm going to give an anthropogenic forcing. Then I'm going to combine both natural and anthropogenic to say this is all the forces. Okay? And we'll see how the models simulate things. Okay? So again, this is time from about before 1900 to there. Clearly, we don't have observations of tropopause height going back to 1900. Okay, so this part is all this model. And then sometime here in the 60s, we started measuring vertical height, vertical temperature profile, and therefore you can estimate the tropopause, right? So the observations come from models, NCEP and ERA, okay? So, when I have only natural forcings, I have this blue line. Again, what's the axis here? This is the anomaly in hectopascals. Please note that negative is up, positive is down, right? Which corresponds to height increase or height decrease. So if I have natural forcings, that includes volcanoes, right? So every time there's a volcano, there's a height decrease, tropopause height decrease. And you see that blue curve going down. Now if I include anthropogenic also, I have this red curve, right? You see that red curve is actually doing the same, decrease in tropopause height when there's a volcanic eruption, and then it recovers, then goes back, another volcano, right? Goes up. But it's the red one that's matching the two observed curves here, okay? And not the blue one. So this is a similar story, yeah.
This pattern consistent over all the questions.
So, for various reasons, it is not easy to diagnose the tropopause height in certain locations. Okay, can you tell me what locations you may not be able to pinpoint the tropopause height? So near poles and wherever you have those jets, right? So in those locations, it's hard to figure out from data exactly where troposphere ends and stratosphere begins. So it's all a mushy. So there's no one height that you can say is a tropopause. Also, there are many ways of defining a tropopause. This is one. This is based on temperature only. You can also define the tropopause based on ozone concentration, for example. You can say where the ozone starts increasing, that's my tropopause. Okay, so because of practical difficulties, this is restricted to the tropical tropopause. So, okay. So at this point, this is a consistent story, right? So not only are we just blindly, running the model and plotting some curve, this is natural, this is anthropogenic, this is the observation. It also has to make physically consistent sense. If you cannot explain through your understanding of physics and chemistry the result, it is not a valid study, right? You have to actually figure out that this is a fairly complicated set of processes that have to happen. Your troposphere has to warm, your stratosphere has to cool in response to CO2, which is a physically consistent thing. And what that does to that tropopause height is actually a fairly tricky thing. You can actually look at what components of the natural and anthropogenic are doing each of these things. Okay, so there's a green curve, which is the well-mixed greenhouse gases. If you look at it, the blue thing, that's the sulfate aerosols. Sulfate aerosols are actually cooling the troposphere and warming the stratosphere, right? So they are actually leading to a decrease in tropopause height. Look at ozone, it's essentially an increase in tropopause height. Solar variability is, not really much effect. Volcanoes, you can see these big round dips. Then if you add all these forces, so when I'm doing individual forcing runs, this is the kind of insight that one can get, okay? So volcano is making a huge impact, but there is an overall trend that is coming from ozone and well-mixed greenhouse gases. Okay? Yeah? Okay. Now, what is this ozone? What's happening with ozone? Stratospheric ozone depletion, right? When you deplete stratospheric ozone, what happens? That is the cause of stratospheric. I want you to tell me what would happen to the temperature due to stratospheric ozone depletion. Increase or decrease? Surface temperature decreases. What happens to stratospheric stratospheric temperature. Let's start with that. It will decrease, right? So there's less ozone means less heat. What happens to tropospheric temperature is there. It will increase. Right? So that will mean a height, tropopause height increase. Okay? So this increased tropopause height is a combination of both stratospheric ozone loss and greenhouse gas increase. Okay? So now you see how all the things that we have done is adding up. Okay? So you can actually look at this.
After 2000, the stratospheric ozone is very increased due to some mitigation of this motion. Then this tropopause will decrease.
It should come back now.
But this the 10 degree of that ozone doesn't disappear only over the polar. No, that is.
See, the depletion of ozone is everywhere. Okay? It is wrong to say that it is only over the poles. It is over the poles that you observe it happen in a short period of time. Because when spring sunlight hits that region, there is an immediate depletion. But if you look at long-term trends, the ozone loss is happening everywhere. Okay? So you can actually, this is looking at the height of tropopause. In fact, there are these, when temperature increases in the troposphere, decreases in the stratosphere, that's a pattern. When temperature increases in the stratosphere and decreases in the troposphere, like volcanic eruption, that's another pattern, right? So these are unique patterns to both CO2 and to volcanic eruptions. You can actually say, are there unique patterns to change of atmospheric temperature because of various factors? Okay? So this is something called a fingerprint. Okay? So a fingerprint is essentially some unique identifier, right? UID is requiring all of you to give the thumbprint and your other biometric identifier. Essentially, it is supposed to say this is so and so. Okay? Now, similarly, if you look at a model response to solar irradiance changes, so these numbers, this is appearing very washed out. So these are all pressure coordinates. Okay, so we are at the surface here. This is the equator. This on your left is. So this is north, and that is south. Okay, equator, north, south, surface, nominal top of the atmosphere. So this is a vertical cross section of the atmosphere, right? So if I run a model and say this is solar radiation only, okay, then it produces a temperature response, mostly warming, through troposphere and stratosphere. Okay? Everywhere that solar radiation is acting to increase temperature, except a little bit of cooling near the poles. Now, when I have volcanoes, again, there's missing colors here. So, it's like we had discussed, going to increase stratospheric temperatures but decrease tropospheric temperatures. Okay? Right? this is the pattern that's slightly different from here because you have a cooling of the troposphere. If you look at greenhouse gases, again as we discussed, increasing tropospheric temperature, more of an increase near tropical mid-troposphere, and a cooling in the stratosphere. Now then there is stratospheric and tropospheric ozone change. What's happening with tropospheric ozone? Does anybody know what? So we talked about stratospheric ozone loss. What's with tropospheric ozone? It's increasing because all your vehicular and other pollution, essentially you're producing NOx, and that's going to produce lots of ozone in the troposphere. So this is again a greenhouse gas. So in the troposphere you have temperature increase. The stratospheric ozone loss is felt most dramatically in the poles, but there's also a stratospheric cooling because of decreased ozone in the stratosphere, right? So this is a pattern that looks very different from this pattern, that looks different from that pattern. Now sulfate aerosol is acting to cool the troposphere, warm the stratosphere, right? So I have 5 individual people. If all of their fingerprints were found in the murder location, they're all suspects, right? Right? So this is what that location looks like. There's all of these fingerprints. Are these different people? Are these single people? And who has done what? Right? So then you can actually say, I'm going to create a fingerprint model changes due to CO2, increase, sulfate aerosols, and stratospheric ozone. This is sort of what it looks like. So this is again going from about 850 hectopascal up to 50 hectopascal. So this is most of the troposphere and the stratosphere, right? And this is what the model simulates. And the observed changes are sort of like this. Okay? So broadly, you're capturing things. Sure, this amount of detail is not seen, but you're able to tell that this pattern is a combination of 3 things that are all anthropogenic, right? So your vertical structure of temperature in the atmosphere has features. Now, this is not the extent of this paper. You can actually see from here how all the details of working through the statistics of making this a rigorous statistical test is carried out, okay? And then some work that I myself have been involved in is changes in the oceans, okay? So one of the changes in the oceans is, okay, so let's see, what would we expect to happen when you increase CO2? What would happen to the surface of the ocean? Rising temperature? Sea surface temperature should rise, right? But if I have a volcano, sea surface temperature would drop, right? At least as long as that radiation is altered, okay? So one of the things we set out to look at is what happens in areas where you have cyclones originating, okay? Now, there are cyclones in the Bay of Bengal and the Arabian Sea, northern Indian Ocean, but the more active regions are the Pacific and the Atlantic, right? Our own cyclones are very short-lived. Southern Indian and Southern Pacific also have cyclones. So what we set out was this is red box is sort of the what is called cyclogenesis, where they are initially formed. When you have warm surface waters, you form these cyclones. So if you look at what happens in the Atlantic and the Pacific cyclogenesis region, the black line again is what the observed temperature is, and the red line is what the average of many with simulations without with and without volcanic forces. Okay, so there's a dashed line which has no volcanic forcing and a solid line with volcanic forcing. And down here you see what the volcanoes do is that depending on the size of the volcano, you have more of an aerosol loading, and that is represented here as a aerosol optical depth. So one of the things that we found was that these regions are all warming and that there is a certain contribution. Not all of the change is due to anthropogenic factors, but there is this, you can actually quantify how much of that increase is due to certain. Okay? So, and then there's also some work on ocean heat content changes, ocean warming. So this is, we started out at the surface, sea surface temperature, and now we're going down in deeper into the ocean. So what we've looked at is what's called the upper ocean. Okay? So we've discussed that how your noise is what's called natural variability or internal variability, right? And your signal is whatever you're trying to detect, the anthropogenic or natural external forces. So if you look at this figure, this is my surface of the ocean, right? And if I go down to 700 meters, this is sort of a measure of how much my temperature can vary. Okay? So this is what my model tells me is how much my temperature can vary. But the red dots are what the observations are. So nearer to the surface of the ocean, there's been a lot of temperature change with respect to the zero temperature. So natural variability means it can go positive or negative, right? Around that zero mean. Okay? Now, all the way down to 700, these temperatures, observed temperatures, have actually increased. Now, if I take the same model and now give it anthropogenic forces, right? I get this sort of area which is hatched green. So this is in the North Atlantic, right? And my model actually predicts a clear separation in the upper layers. You see this green hatched area overlaps the blue to a large extent, which means I can't really separate natural from anthropogenic change there. But up here, there is a change. There is a clear separation of what's natural and what's anthropogenic. And my observed is better explained in that green hatched area than the blue hatched area. It's actually getting that form. So my model is telling me that this observation is due to anthropogenic forces. Now I can do this in all of the ocean basins, right? So there's the North Atlantic that we just saw. North Pacific, North Indian, Southern Indian Ocean, Pacific. Okay? In each basin there is a clear separation near the upper levels, and also the observations fit better with the anthropogenically forced variations. Okay? So, now in the North Indian and North Pacific, even the observations show warming only down to 125 or so, whereas in the North Atlantic, the warming goes all the way down to 700 meters. Okay? Even in the South Atlantic, there's clear warming, whereas in the Indian Pacific, it's mostly in the upper 200 meters. Why? Why would heat go so much more in the Atlantic than in the Pacific? It's the deep water formation, the conveyor belt that. No. So when you have sites where convection occurs in the ocean, right? You're essentially pulling down water all the way to depth. So that we can transport a lot more heat than in the other ocean basins where you don't have that sort of deep overturning circulation. Okay? So, even here the physical reasoning has to be consistent with what is known about the climate system. Okay? So, this is, if you look at individual, we use a single model, both in terms of using the natural internal variability and for the warming or anthropogenically forced climate change runs. Okay? Now, you can choose different models. How do you know? How do you know this blue region is correct? How do you know it is not fully white? Because we saw that it's only separated from the green in this part. How do you know that it's not even whiter at the surface? You have to be able to estimate the correct variability. So we, this is not a good predictor. So again, we've lost some color, but essentially in this, we are looking at the total ocean heat content down to 700 meters in the upper ocean only. So this is a tremendous amount of energy. So it's all raised to the 10 to the 22 joules, right? So the observed is this black curve, and then you have the blue line, which is the natural forcing only, and the orange, pink lines, which is the natural anthropogenic. So again, a similar kind of a figure, but what we did, okay, you take these blue lines, which is just the natural forcing, right? So if you have natural forcing only, what we do is take segments. Okay, I'm going to take 11-year or 10-year segment. Give me 1 decade worth of temperature increase, right? Then take another 10-year period, another 10-year. So I keep taking 10-year segments and calculating what is the trend or slope. Okay? Because you can have 1 10-year where it increases, another 10-year where you have a decrease, right? That's your natural variation. So if I take a sample of all the 10-year trends, all the 11-year trends, 12-year trends, and so on, and I'm going to take all the 30-year, 40-year, 50-year, right? All the way from 1950, I can take trends. to the end of the record. Okay? So if I do that, then what one can find is that as your length of trend is small, then you will get some years are showing positive trend, some years some bits or segments are showing negative trend, right? So that is my noise, right? Lot of up and down means lot of positive and negative trends. So my noise amplitude will be large. As I take longer and longer segments in that time series, my noise actually goes down. Okay? So I have one segment, right, that's in the observer, but by taking longer and longer trend lengths, I'm actually reducing the noise, thereby increasing the signal to noise ratio. Okay? So what that means is there are many curves here, it's not important. Is multi-model standard deviation. So I don't have time to fully explain all the intricacies. This one figure can take you weeks to generate. Okay? But, so there are many models. Each one of them can give different. So I have to take the collective wisdom of all the models, not just one model like I previously showed. Okay? So what this means is that I can actually plot something called the signal to noise ratio. Okay? By starting at a particular year, 1970, then I said I'm going to take 11-year trend and 11-year signal. I've already calculated noise, so I'm going to calculate the signal to noise. Okay? And if that signal to noise ratio is more than this black line, then it is statistically significant at a 1% level. There's actually a gray line here, where you can see that's the level at which it's a 5% significance. So, over time, it looks like all of these have crossed. So, in fact, as early as 1980 or 85, in terms of detectability and attributability, that change occurred. Human influence on the ocean heat content was evident in the 1980s, but we didn't have the observations collected and processed in order to know that. Okay? So, climate change has been happening long enough now that some parts of the system have emerged from the noise. Okay? Just like some parts closer to the equator where the noise is small, they will emerge from the signal will emerge from the noise earlier than near the poles. Certain parts of the climate system like this have already emerged from the noise. Okay? So basically, it's not just a statistical exercise. You have to have physical consistency with what should happen based on theoretical considerations, right? If your model does something strange, your observations are doing something else, clearly that's not a situation where you can start doing a detection and attribution, right? Because it's a process. If you haven't understood it, it should not, right? So, there are many temperature-related fields, global scale temperatures, regional scale temperatures, vertical profile, which we discussed a little bit, global ocean heat content, stratospheric and tropospheric temperatures at various bands, height of tropopause we saw, vertical structure of upper ocean temperatures we saw, sea surface temperatures in the hurricane or cyclone formation regions. Then we didn't touch upon Arctic and Antarctic temperatures. But then there are also circulation-based things. Things like what happens to sea level pressure when you start changing climate, continental scale runoff, atmospheric water vapor, especially over oceans. What do you expect to happen? Increase. Okay? When you start increasing temperature and you have over oceans higher saturation vapor pressure, and therefore you have to have more water, right? Surface specific humidity, zonal average precipitation. Why would precipitation increase? So this is an intensification of the hydrological cycle, right? So if you have more water vapor in the atmosphere, you will cycle through more water vapor, right? So there are regions in the western United States where they've done some specific Arctic sea ice, ocean salinity, and river runoff in India. I think people in this room have actually worked on it, one of your fellow attendees. So here in IISc Bangalore, there's been work, river runoff in India. Okay? So what happens? Essentially, you have an intensification of the hydrological cycle, more rainfall, which means more runoff, which means over oceans, you will see it in the salinity structure, where you have more E minus P, more positive E minus P, you will end up with lower salinity. Where you have more negative E minus P, you will have low salinity. Okay? Similarly, over land. So, the reason something like a tropopause height, or a salinity structure, or a river runoff, these are, and ocean heat content also. Why these become important is because they integrate some changes. Okay? So, rainfall is sort of a spot variable, right? But all that rainfall over a region eventually shows up in your runoff in some measure, right? So it sort of integrates what happens over a large area. So whenever you have a variable that is integrating something that's occurring from many processes, you can end up. So there is a sort of a consistency in that story, right? So just to summarize and close up, climate is changing and has changed due to anthropogenic influences, okay? And you can see that from climate models. Climate models are by no means perfect, but especially global, hemispheric, maybe continental scales, they are telling us reasonably accurate information. Now, would you start using it to look for climate change in your own particular area? It's still too early for that, but they are definitely less skillful at that local and regional scale. So before we start using it to detect climate change at local levels, there's still much to be done. But this is also changing very fast. So stay tuned. Okay, I think I've finished just about on time. Any questions? Either perfect understanding or perfect hunger. It's increasing in stratosphere also. Yeah. PBL, I don't know actually. I mean, I think this planet